Good evening, everyone, and a warm welcome to this webinar titled Nonlinear Material Modeling, an Introduction. Today, I'm going to walk you through testing and the very specialized area in finite element analysis. So about what exactly the material nonlinearity is and how material nonlinearity works, and how the materials are classified based on the behavior and the orientation, and the hardening guidelines and certain material mathematical models that are available in commercial FEA tools that are available in the market. And we're going to talk about how to decide whether we go with the linear elastic or any other nonlinear methodology. Then quickly walk you through the case studies of the automotive industry, and we'll talk about the global mega trends, and of course, the current job market survey, which I did, and we'll talk about the career prospects of pursuing your career in finite element analysis with the skill development plan based on the current organization requirements. And of course, learning is a lifelong process. So we're going to talk about a little bit on continuing professional development, ending with a question and answer session. Everybody might have been using materials in our daily lives. There is no object or a product or a part which is made without any material in the world. So material nonlinearity, or understanding how the material behaves and the significance of materials used in the product design is very, very crucial. So that's what determines the strength of the material and also the durability, as well as the reliability of that material used in any particular product, be it an automotive component or the full vehicle or the aerospace component, whether it's a composite material or a reinforced polymer, or even the metals and other non-metals. So what exactly material nonlinearity is? You must have gone through, let's do a quick recap of what you might have studied in your colleges during your 4th or 5th semester about the strength of materials. You see the stress strain curve of a mild steel, as you could see here. So everybody knows that when you apply an external load to any particular specimen and then measure the stress and the strain accordingly, this is how your curve is going to be. Now, initially from the point O to A or up to B, then you have elastic limit up to A, and then this is where exactly the stress is proportional to the strain. When you apply the load within this region, the stress is going to be proportional to the strain. So when you measure beyond that, it definitely loses its proportionality because it's beyond yielding. It gets into a slightly elastic plastic zone, and then with a slight permanent deformation. Then further, if we just stretch the material, and it will further get into the plastic deformation zone, a permanent deformation zone. So anything beyond point A is going to be the nonlinear part beyond plastic deformation. So then obviously it goes up to the necking, which is a D, and of course where you hit the ultimate tensile stress, and post necking is what the fracture happens. Now, it can have even temperature into effects. When the temperature gets into picture, then the phenomenon of creep will dominate. We're going to talk about those terminologies in the following slides. So when you subject a particular specimen under an external load, the response of the structure is going to be nonlinear, in the sense beyond the elastic limit, it is going to be nonlinear because it is no longer going to be linear, as you could see with the blue dotted line. So it is not going to be linear. It is just going to go beyond the yield limit. This is how it behaves, as you could see in the laser pointer on the screen. So it's not only the material behavior and the kind of the force that you impose. Force is nothing but the external load which you're talking about, and its corresponding displacement. So you keep increasing the loads in terms of increments. That's what we do in nonlinear analysis. So those load steps and its corresponding displacements are also nonlinear in nature. It is not going to be proportional. So this is how it impacts geometry material and contacts in the assembly, because there is going to be a stiffness change the way when the material behaves. So due to the stiffness change, it impacts the geometry that you use in a particular product, and also the material that you use, and also the contacts in the assembly. Now we are going to focus a little more on the material part, which is used in the assembly due to the stiffness change. The governing equations had been the governing equation, the basic governing equation is Kx equals F, which is been derived. The motivation behind deriving this is the spring load. If you could just imagine a spring within it, at one at the fixed end, and the other, like you could see it here. So this is the fixed end. You have the spring, and it's at free state, and you don't stretch it. So whereas the same spring, if it's at free state, I stretch it beyond. So this deformation of that particular spring, or X, is going to be the displacement. So what, and the load that you're going to apply, which is nothing but your F, that's the pull load which you're going to pull the spring. So this is the motivation to for defining the governing equation for finite element methods. So that way, K is the stiffness that characterizes the spring. So in the finite element methods, if such kind of analogy is used, it is very, very useful to determine the unknowns. So that's why we have Kx equals to F. But the difference between the linear statics and nonlinear statics is just that your stiffness remains constant. Over here, the stiffness does not remain constant. It is dependent on the displacement. The moment when you apply the force in increments, the displacement is going to be different at every load step. And so as the stiffness is dependent on the displacement. So K being the global stiffness matrix, which is dependent on whichever the whatever may be the displacement is with the applied load from the external forces vector, which is F. Now, one question arises in our mind: why do we need material nonlinearity? Because we have linear statics, it's quite easy to solve the problems, and we don't have to worry about it because the stiffness remains constant. There is no problem. There's only one magnitude of load which we are going to apply, which is in static condition, and we are going to get the results, and we are going to check the stresses and check with respect to the yield. What is the, if you're dealing with the ductile material, you compare it with the yield limit, and if you're dealing with the brittle material, you compare it with the ultimate tensile strength, and accordingly you plot the stresses. If it's for the yield, you actually plot it for von Mises criterion, and if it's for the brittle, obviously you plot it for the max principal strain. So why we need a nonlinear analysis is because your linear statics will not be able to capture the actual phenomenon that happens beyond the elastic limit. As we had seen in the graph, like beyond the elastic limit, it is definitely not going to be linear as a blue dotted line. And it's going to take its a characteristic curve based on the behavior. So nonlinearity eliminates such kind of uncertainty which cannot be captured by linear statics. However, it consumes more time to solve the problems. And at the same time, it also needs specialization based on the knowledge that you gain and the experience that you gain to solve any nonlinear problem, be it a material geometry or the contact. So on the right-hand side, you see this, there is a kind of a rubber boot, which you must have seen in a car with a gear console where you shift your gears in a passenger car. So if you could see, this is a kind of a hyperelastic material which has been used. Now, there are two things over here. One is the material nonlinearity has been included in it, and the other one is contact nonlinearity. Why contact nonlinearity is because when you just shift your gear console, this is only to close the enclosure of the gear console with a rubber so that it prevents the dust or air that gets into the console. And the second part is it's a rubber being flexible so it can retain its original position once it's unloaded. And rubber being elastic in nature or elastomeric in nature, so this kind of, it makes a self contact with its own layers. That's why contact nonlinearity also comes into picture. Now, whatever that you see on the right-hand side, as you could see in the pointer here, so it's a gear contact which you might have seen in different applications, especially in planetary gear sets used in the transmission system, which drives your wheels in a car or a truck or a bus. So here the contact nonlinearities come into picture. However, the materials used for the gears also matters if it's really of a concern with the material. So if we specifically talk about nonlinearity, we have geometrical, material, and contact classification. But since our focus is more on material, it has been classified into 3 categories. One is beyond elastic limit, what is going to happen to any metal, whether it's a steel, any other metal, aluminum. So that is one category where you will just analyze how the material is going to behave beyond elastic limit. And then the second category is within the elastic limit, which is about non-metals. Maybe it's a plastic material. And the third category is about the creep phenomenon. A creep is a kind of a progressive deformation of a material. Although beyond a particular point, your stress will not increase further, but your strain keeps developing. But it's a long time process. That's what the creep is all about. How the material nonlinearity is going to work. So as I told you earlier, take a material specimen, you subject it to an external load. The following behavior is definitely observed during measurement, whether you use universal testing machine, whether it is going to be a uniaxial or a biaxial or a multi-axial testing machines. And this is what every test engineer observes by choosing a particular material and to understand how that material behaves and to characterize that particular material. What is its fatigue limit? What is its durability of that particular material? So they undergo a material testing called universal testing machine, using universal testing machine. You must have heard about this term in your colleges. So the first part that they observe is when you keep loading the specimen is the elastic part, wherein everybody knows that stress is going to be proportional to strain. And the second part, which we are going to talk about, is the plastic plateau. Plastic strain develops with no change in material stress. This is what exactly is said, like beyond a particular point, no matter how much ever the stress does not increase, it remains constant. However, the strain keeps developing, the strain it keeps developing inside the particular material. So, and then finally, the beauty of the material steel is that it can still yield while increasing strain. That's the beauty of steel. So that's why most of the times steel is the most predominant material used in metal category for any applications within the automotive industry or even in the mechanical industries. So we also talk about plastic redistribution. There is something called plastic adjustment. So I'll come to this point. I'm going to give you a very good example of to understand what this plastic adjustment or redistribution is all about in the upcoming slide. So finally, the most important thing that we need to check for is you do a linear statics, you got your stresses, you compare the stresses with your yield limit if you're dealing with a ductile material, and you feel that, okay, so my stresses are too high. You're not able to believe that the stresses can be that high because even your basic beam calculation or analytical method might help you a little bit on the analytical results, which is way far away from what simulation results are. But definitely there will be a deviation between analytical and simulation. However, if you find the stresses to be unrealistic, you have to check few things beyond an elastic limit. How much high is that value is worth looking at it in linear statics, because linear statics is not going to give you the realistic picture beyond the elastic limit. So in that case, we need to check the maximum plastic strain value wherever in the part or the product that you're designing, and check, and there are certain threshold values or some kind of a thumb rule guidelines where if you could check your plastic strain value, if it is going to be less than 5%, and I believe that, okay, fine, so you can take a decision based on that. So this is what I was talking about. So on the left-hand side, you could see this is this is what exactly happens when you load the material in universal testing machine. So this is the elastic part, and plastic plateau is beyond the elastic limit. You keep having certain fluctuations of the stresses, but almost remains kind of constant stress. But your strain keeps developing. Your stress does not increase further. It remains constant over a period of strain. So when the strain keeps developing and beyond that particular point, then once again the stress keeps increasing over and over as the strain increases. But this time it strengthens the deformation. Once the permanent deformation is set onto the material, it strengthens based on the strain energy. That's what you must have heard about the terms called work hardening, strain hardening. It depends on the strain rate, the rate at which the strain gets developed over a period of time. So finally, it hits the necking. That's where you start having a light kind of a possibility where the internal crystal structure of the material starts deteriorating. And then finally, it gives up beyond a particular stretch of the external load, and it starts cracking right from the surface, and it ruptures the material. So if you could see on the right-hand side figure, so this is what we call it as maximum allowed plastic strain for any particular material. So you need to check this in the region of the interest in case if the stresses are too high, where you're, if you do the linear statics, that is going to help you decide to go with the nonlinear analysis. So the materials are classified based on various parameters. As you all know that when you subject the load, the material properties are going to behave in a very different manner, which means the material properties, let's say your Young's modulus, and yes, obviously your other parameters like toughness, your rigidity. So all more kinds of more properties gets affected because it keeps changing. The stiffness keeps changing because of this change in material properties, and definitely it is going to happen with the permanent deformation. So based on that, certain mathematical models have been developed by the engineers and researchers in the past in the past 20 years with a lot of developments to say that how can I have a material characteristic of a particular a model of a material which can actually get deformed during the testing. So that kind of material models are nothing but a mathematical models that represents a set of equations. So as of now, you can just understand that a set of equations called constitutive equations. So depending on the number of equations gets your and the number of unknowns will be calculated. So this constitutive equations, why we call it as constitutive, because these are the equations that keep describing the relationship between the stress and the strain at every point of time during the solving, because your stress and strain is not going to be linear here. It keeps changing, or perhaps per se the strain rates as well. So the kind of constants which had been used in the constitutive equations are nothing but the material parameters. They call it as material parameters. So where do we get these constants from? So how do we characterize a material? Because we need these constants as inputs. So the best way to get the constants of materials is to talk to your supplier. If you're working for an OEM, or if you're working for a supplier, you talk to your sub-supplier or contractor and ask him to test that particular material, and you get certain constants based on that. And then you should do a kind of the constants that you fit into this model and try to get the curve as that of the testing method, the stress strain curve, and use it as input for your nonlinear analysis. The material is also classified based on the behavior. That's one. On the other hand, it also is classified. You must have heard about various terms, and it is based on the orientation of that particular material properties. So when you talk about isotropic, the properties are going to be uniform in any particular direction. That's going to be your isotropic material. Anything which is non-uniform, which keeps varying in any particular direction, like X, Y, or Z, is going to be anisotropic. And orthotropic is very specific case of an anisotropic material. Anyways, the variation of the material properties will be there in any direction. However, why orthotropic is because when as you can understand by the word ortho means orthogonal, which is a 90-degree when you compare one plane to the other. So although the variation is there between the two planes, anything which is a 90-degree between the two planes that you study, and that particular property change is known as orthotropic. And homogeneous is definitely going to be the same. The properties are definitely going to be uniform. However, it need not necessarily be all the homogeneous materials need not be isotropic. So homogeneity in the sense it's everywhere, it's uniform. And heterogeneous is about it's a kind of different materials. It's a mix of materials that you use. So on the bottom left-hand side, you could see the materials classified based on the linear elastic. When you load a particular material, it is going to be linear, as you could see my laser pointer. And at some point of time, let's say beyond when you reach the elastic limit, you unload that, it is going to fall back or on the same linear path when it retains its original position. So this is said to be linear elastic in nature. Now, and if you move on to the nonlinear part, what happens to this one, the graph A? So when you start doing, so there is a linearity over here, but it is not extrapolated to see the nonlinearity. So your linearity ends somewhere here, but when you start loading beyond a particular point, so your stress is no more proportional to strain, and it keeps varying. But when you unload that particular material, unload the specimen, which means remove the load after stretching at certain point of time. It also falls back on the same path, but it takes time to retain its original position because there is some sort of permanent deformation set. And when we talk about the graph B, this is quite interesting. It's a very special material which belongs to the elastic material. However, when it starts loading, and there is a kind of when you remove the load suddenly at certain point, so it is not going to follow the same path. You must have heard about the word hysteresis, probably in your magnetism. So when you remove that, definitely it is going to have a different characteristic of stress strain. However, it will reach the point 0 with no plastic strains left. Will be very, very minimum plastic strains, but those plastic strains are of high importance when we deal with the hysteresis elastic material. Whereas in the case of plastic materials, it is not the same. When you load it and when you unload it, it is not going to follow the same path, but it is going to be very much linear, but it will allow the plastic strain to be plotted. So it is not going to fall back at 0, and this leaves some plastic strain in the material. This is how the plastic materials behave. So when we talk about the material characteristics, which means like a material that you see it in your daily life that, okay, it is going to crack, it is going to break. If you observe it, the crack always begins at the surface. So when we talk about the material characteristics, we just go into take a deep dive into the material specimen. If you could see it, in a particular material, how that develops is when your dotted lines is an elastic, you will have an initial yield surface, which means you can just imagine. And beyond that particular limit is what this changes that you and which you see it. So it reaches a zone where the yield surface will still be there after loading. So that brings into the plastic deformation if you don't unload it, and it goes on with the permanent deformation. There are also other materials which you can talk about, non-viscous materials. Your stresses is not going, it keeps changing with respect to the time. For example, the bushes that you use it to place an IC engine onto the chassis in a particular vehicle, the bushes, some kind of a material, a special metallic bushes. So certain materials absorb energy and then try to withstand the shock and then release less shock to the structure that is connected to. So this way, it reduces the vibration in any particular system that you use. You can even imagine your car. So your stress keeps changing and then it remains constant over a period of time. And if you talk about viscoelastomers, it's a special material which has been used. You must have not observed, but you can observe it moving forward. So there is some kind of an adhesive or a kind of material which is used on the floor of your car, probably at the when you go to the boot space of your car, there would be certain shapes on that particular surface. All this is done, which is based on some kind of viscoelastic fitted inside or onto the top of it, and then they would have another layer. So this reduces dampening, which reduces the vibration, which in turn reduces the noise levels. So it also remains constant over a period of time, the stress, and it keeps varying depending on the characteristics of each viscoelastic. So creeping is a phenomenon which we spoke about. Although the stress is going to be constant over a period of time, definitely your strain is not going to be constant. It keeps increasing further over a period of time. That's why we call it as a long process. It especially happens at elevated temperatures. Also, if there is any change in room temperature where you had kept that specimen. You must have all be wondering that why the rocks that you see, the mountains or the rocks, if you could have seen in the history. So by nature itself, like it has got a creep phenomenon. So that's how a huge rock breaks up into small rocks, which we might have not observed, and it takes years together that happens. But if you go to the tourist spots or mountaineering, you can observe this. Everything happens at the material crystal structure, which takes time because of your sun's radiation. Everything, the creep phenomenon elevates at high temperature. It starts developing huge strain. At some point of time, it cracks and the huge rock breaks up into small pieces of rock, which is a finite measured rock, and it keeps displacing, and the rock rolling happens in the mountains. If you would have observed, or even you could have heard about it, you can take a deep dive into it for more information, as the geologists observe such kind of creep phenomenon. So creep is not going to happen all of a sudden that you stretch it extremely well and no subject to temperature dependency. It's not going to happen. So this is a very dangerous phenomenon if you leave this unattended in a particular product, if it's experienced to high temperature zones. So the images that you see on the right hand side is a special hyperelastic medium. It's a gasket or a seal. You must have heard about the seal. Seal is very important material. It's made of a special hyperelastic medium or a rubber compound where it can deform itself and then retains its original position or adjusts its shape. Now, why hyperelastic material is used is because it is used in seals, and the seal is always used to prevent any particular fluid leakage that enters into the structure. In a basic daily lives, you see the taps that you use it in the bathrooms, and you close the valve, your water does not drop. But if you would have seen in a damaged taps, your water keeps dropping even though the valve is closed. This is happening because the seal that you use, or you can even call it as a washer in a general language. So that washer is a kind of a medium. It used to prevent the leakage, although there is a whole lush of pressure on the other side, although the valve is closed, because your water is of constant supply when you have the water in your tank at your home. So when the seal starts deteriorating, you get such kind of leaks. So seal, that's a daily life example, but you have the seals everywhere. It is used in electronics, it's used in automotive engineering, it's used in almost in every engineering industry, marine, aerospace. So seal is the one which prevents air, dust. So automotive seals are the major thing and when you make the cars or trucks. And this one that you see is a contact kind of a shaft wherein a small pinion gear inserts into it, kind of a press fit that it gets inserted it. Press fit is a sort of manufacturing operation, and that time the material should not deform much, and it also experiences contact nonlinearity. So as we had seen, creep is a phenomenon of time-dependent strain at a constant stress. And it's observed in most engineering material, especially the metals elevated temperatures. And its major applications could be, you can experience creep in high polymer plastics, your concrete, and even the solid propellant used in rocket motors.